Hello, so welcome back to another video. Well, this is the last video of our module 3, that is modeling. And in this video, we'll be covering the assignment on resampling method. So without further ado, let's get started with our question 1. Question 1 says, perform validation using 50% of the data as training and rest of the 50% as test. So we will be using auto dataset that is available in ISLR package. It's a data frame with 392 observations on 9 variables. So let's read the data and then we can check the structure of the data. Now, as you can see in the structure, there are 9 variables. We have mpg, that is miles per gallon. We have cylinders, which is between 4 and 8. We have engine displacement, then horsepower, then weight of the vehicle, which is in pounds, then acceleration, then model year, then origin of car, which is either American, European or Japanese, and the last variable is name of the vehicle. Now that we have understood the data a little bit, so let's move on to the next step and create the training data set. So first we will set the seed as shown here and then create a train variable using the sample command. So the first argument is 392, which is the total number of observations. Then the sample size is 196. So basically this time we are creating a training variable with 50% of the observations. Earlier we had used a 70-30 split, and I also said that it could be 80-20 or any other combination. After this, let's fit the model. So we will regress mpg onto horsepower. So here we are doing simple linear regression for demonstrating the method. Then the second argument is the data, which is our auto data set. And then we'll use subset is equal to train, which will basically subset the training data set. So either we can directly subset our data set using the name of the data set and then mention train within the square brackets. Or we can write it like this, mention the data separately and then use subset function to subset the training variable. After this, we will store it in the variable lm.fit. Then we'll make the prediction using the predict function. So the first argument will be our model and the second argument will be our test data. So for test data, we'll just have to put a minus sign before the train variable and then use square brackets to subset the auto data set. Then we can run this and we'll store it in the variable pred1. After the prediction, we can calculate MSE. So we will use the test data here and then we'll subtract the predicted results which are stored in pred1. Then we will square it and then we'll take the mean, which will give us the MSE. Now as you can see, our MSE is coming out to be 28. Now in the explanation, the second point says, we can also try quadratic fit instead of linear fit and check if the error improves. So we will try quadratic fit now. So for quadratic fit, we just have to raise the horsepower variable to second degree using the polynomial function. And rest of the arguments remains the same. We will run this and store it in the variable lm.fit.quad. After this, we will make the prediction using the test data and then we'll find the MSE as we did above. Now you can see our validation set error has reduced and it is coming out to be 18.71. Now as per the explanation, it says one possibility is that our data is better defined by nonlinear model. That is the reason on using the quadratic fit, our error has reduced. Now there are two major drawbacks of validation approach as listed here. The first drawback is the validation estimate of the test error rate can be highly variable, depending on precisely which observations are included in the training set and which observations are included in the validation set. Second point says, we get less training data
for training our model, which can lead to overestimation of test error rate, as statistical methods tend to perform worse when trained on less observations. So these are the two major drawbacks of validation approach. So we will move to question 2. It says perform leave one out cross validation. Now what is leave one out cross validation? Here also we split the data into two sets. However, one observation is kept as test set and remaining all observations are used for training. Then we repeat this process all over for all observations. This way, leave one out cross validation addresses the above two drawbacks that we observed in the validation approach. So this means it is a better method. Now let's see how do we implement it. So we will use GLM function for this. So we will first load the boot library. Boot library has the cv.glm function. So we can use cv.glm function which performs leave one out cross validation. And to use cv.glm function, we have to first use glm function. So we will build the model using the glm function and then cross validate using cv.glm function. So glm will be used in the same way as lm function. We regress mpg onto horsepower and then store it in the variable glm.fit. After this, we will use cv.glm function. So the first argument will be the data and second argument will be our model. So cv.glm function will calculate the cross validation error. It will split the data in k folds, where k by default equals to the number of observations. This way, leave one out cross validation will be performed. Now there is an explanation given here. So let's read the explanation. First point says, the most important result of our output is delta. You can check the other outputs as well using cv.error function, but right now that is not important for us. So we'll keep our focus on delta and understand it. Now here the first component of delta is the average mean squared error that we obtain from doing k-fold CV. So if you see, there are two components of delta which are printed in the output. So the first component of delta is the average mean squared error that we obtain from doing k-fold CV. Then the second component of delta is the average mean squared error that we obtain from doing k-fold CV, but with a bias correction. Now what is bias correction? A biased estimator is one which delivers an estimate which is consistently different from the parameter to be estimated. So when an estimator is known to be biased, it is sometimes possible by other means to estimate the bias and then modify the estimator by subtracting the estimated bias from the original estimate. This procedure is called bias correction. It is done with the intent of improving the estimate. Now if you find it a little bit technical, then you don't have to get into the details of it. Just understand that the bias estimator is used with the intent of improving the estimate. So we will be using first delta to assess the performance of our model. Now we will move to next question. Next question says, perform k-fold cross validation. So here we will do a 10-fold cross validation, which means we will split the dataset 10 times into the folds. Now there could be any number of folds. We are just randomly selecting 10-fold cross validation. So we will first set the seed and then we'll create an empty vector. This vector will store the cross validation error. Now to perform k-fold cross validation, we can simply use cv.glm function and mention k is equal to 10. But we are doing one additional step. We are raising the polynomial degree of the horsepower variable and see if there is any impact of it on the CV error. So for doing this, we will have to use for loop. So we will run the loop from 1 to 5, which means we will vary the degree of polynomial from 1 to 5. Then we will create the model using glm function. So here, as you can see, we have used poly function with horsepower and the degree is mentioned as I. So it will start from 1, then create the model, perform 10-fold CV, then store the error and then go back to the loop and increment the value of I. So in the next step, the polynomial degree of the horsepower will be 2 and rest of the process will remain same. Also, if you have noticed, we are only storing first delta because as we discussed above, we only need first delta to check our results and compare the model. After this, we will run this loop and we will print our CV errors. Now we can see here, as the degree of polynomial is getting increased, there is a decrease in the CV error. Also, there is a sharp decrease from 1 to 2 degree, and then there is a marginal decrease which can be observed from degree 2 to degree 5. So it might reduce further if we keep on increasing the degree of polynomial, but I hope you have understood the intent behind doing it. We could also have varied this degree of polynomial in leave one out cross validation as well, but in general, leave one out cross validation would be slower than k-fold. So that is the reason I did not take many parameters in leave one out cross validation. So that is how you perform k-fold cross validation. Now we will move to next question, which says perform bootstrapping. Now we already know bootstrapping simply means taking multiple samples using the sample datasets with replacement and then generate B training datasets. It is a generic approach and it is applicable on wide variety of statistical methods. In bootstrapping, what we do is we make n different samples from our datasets and find alpha for each sample and then take the standard error of all alphas. So basically alpha is the statistic of interest. It could be anything. Say in linear regression, it could be the coefficients, etc. Now instead of doing this over and over again n times, we can use boot function. So let's see how we do it. Now to perform bootstrapping, we will again load the required library and attach the data. Now first we will have to create a function alpha which will return the statistic of interest, which in the case of linear regression will be the coefficients. So we have created a function using the function command. This function will take two arguments. First is the data and second is the index, which basically means how many observations to include in it. And then it will return the coefficients of linear regression model. So the arguments for linear regression will remain the same. So for better understanding, I'll explain what is the use of alpha function. So if we refer to sample 1, we'll use alpha function. Then the first argument will be our data. And then in place of index, we will mention sample. The first argument will be 392, which are random observations. And then second argument will be 392 again, and replace is equal to true. So basically we are generating a sample of 392 observations from 392 random observation by putting replace is equal to true. So this way we'll calculate coefficient of our first sample. So these are the coefficients which are calculated. Similarly, we can create another sample and we can calculate intercept and horsepower again. Now we can keep on generating the samples in this fashion and then calculate the standard error for all the coefficients. So this is how bootstrapping works. But instead of doing this manually, we can use the boot function to carry out this task. So let's see how do we use boot function. Now before that, I have included an explanation for the working of alpha function that I have just explained. Still, if you have any doubt, you can pause the screen and you can read it through. Now for the boot function, the first argument is the data, and then the second argument would be the function that we have created, which is alpha.fn, and then the third argument would be the number of samples that are to be generated. So we are mentioning 1000. So boot function will generate 1000 samples just like we generated 2 samples above, and then it will calculate the standard error of the coefficients. So we will run this and we'll get our result printed here. Now you can see here the intercept and coefficients along with the standard error are printed here. For intercept, standard error is 0.84 and for the coefficient it is 0.0074. So that is how bootstrapping works. Now we will move to question 4b. It says check the results by performing the standard linear regression and compare it with our above output. So we will directly calculate the coefficients using the summary function, and within the summary function we will write our linear regression model. That is, we will regress MPG on horsepower and give our data to it, and then using the dollar sign we will subset the coefficients from summary output. We will run this and our intercept and coefficient is printed here. Now if you see, the standard error of coefficient and the intercept term is different from the bootstrap results. Now why they are different, there is a reason behind it, but that is beyond the scope of this assignment. However, if you are interested to know the reason, then you can read the ISLR guide. This example is given on page 196. Alright guys, so that is all from resampling methods. We have learned 4 different approaches here: the validation approach, then leave one out cross validation, then k-fold cross validation, and finally bootstrapping. This will form a basic understanding of resampling methods, and we can use them in future to make really powerful models. So with this, we have come to an end of this module, guys. This was the last assignment in this module. I hope you have benefited from all these videos of theories and assignment. And if you still have any doubts, watch the videos again. Do some research on the internet. But I've tried to break down each and every bit of the code. I hope you can appreciate it. Now in the upcoming videos, we'll be discussing advanced modeling techniques. I hope you guys are excited about it. Thank you very much for watching the videos, guys. If you liked the videos and found it helpful, do support me by liking the video, sharing it with your friends, and do not forget to subscribe. Now I'll see you in the next video. Keep learning and have a great day.